Hello, good afternoon, everybody. I'm Srikara Pranesh from the Department of Mathematics, University of Manchester, one of the co-organizers of this two-part mini-symposium, where we have made an attempt to bring together people from various aspects of scientific computing who are employing low-precision floating-point arithmetic. So we have speakers from numerical analysis, software development, and applications as well, where they would like to share their experiences and their insights into using this new development in scientific computing. So just a note to the speakers. So the talk is for 20 minutes plus 5 minutes for questions. So when you're up 15 minutes, I'm going to stand up, and it just indicates that there is 5 more minutes left. Okay, so the first talk is mine, and Theo has kindly agreed to stand up if I'm going over time. Okay. Yeah. Like I mentioned, so the basic question most of the speakers of this mini symposium are trying to answer is, how can we use this low precision floating point formats to speed up our various applications? So I come from a numerical linear algebra background, so I have another additional criterion as well. I don't want to compromise in any way on the quality of the solution which I'm getting. So essentially what I mean is, so you replace the code which you were using earlier, just that your code runs faster, but the quality of answer which you were getting previously, that stays the same. So I will try to answer how that can be done for the case of solving a linear system of equations when your matrix is symmetric and positive definite. So just to give a little bit of background, so why is this important? Why is talking about low precision floating point formats important? So this plot I have generated using the top 500 lists. So as you can see, since I've just started it from 2016, that's because that's when the deep learning thing started. Okay, so one thing which you can observe is the number of systems out of the top 500 which have accelerators in them is increasing. But what is even more exciting is, rather, I would say, that the number of systems which have hardware in it, which has an FP16 support, is increasing as well. That's the purple line here, purple line. Okay, so this particular trend makes the question of using low precision in your applications quite relevant at this point of time. Okay, so just to make it clear, so the question which I'm trying to address in this particular talk is, how can you solve a linear system of equation in a fast way when your matrix is symmetric and positive definite? So this particular question, for the case of a general matrix, that is when A is a general n by n matrix, can be answered by using GMRS-based iterative refinement. Many of you might have heard about it, but just for the sake of completeness, I'll brush through what it actually is. So it's a variant of the classical iterative refinement, but with two stark differences. That is, you can use low precision floating point formats, and apart from that, the correction equation is solved using GMRS. So why would this work? So you can see here, that's the first step here, is to do an LU factorization in low precision and find an approximate solution to it. And then you use that low precision factor as a preconditioner to refine the solution to whatever quality you would want. Why should this work? So this can work because this particular step is order n cubed, and everything else after that is order n squared. So if the number of steps required to refine your solution to the required quality is small, then most of the work is done in low precision itself, and you can get enormous amounts of speed ups. So this is in fact being demonstrated by a work by Jack's group, where they demonstrated that this particular algorithm is in fact 4 times faster than the state-of-the-art pure double precision solver, and moreover, it is 80% energy efficient as well. Just to clarify, I mentioned that it uses multiple floating point precisions. So that's what I have mentioned here. So when I say UF, it means it's the precision in which the matrix is factorized. U is the precision in which your matrix is given. And UR is the precision in which you compute the residual, or if it is too much of jargon, just think of it as the precision in which you measure the quality of the solution which you have already computed. Okay, so this is for a general matrix. Okay, so the answer to the question which I posed earlier, what is a fast way to solve a symmetric, positive, definite linear system, seems pretty obvious from this algorithm. That is, if you are doing LU factorization for a general matrix, replace it by Cholesky factorization. And if you were using GMRES to refine your solution to required quality, replace it by preconditioned conjugate gradient. Okay. Even though that's quite obvious and quite intuitive, this might not work always. So the reason being twofold. So the first thing is your Cholesky factorization might not itself succeed. That's because in a floating point system, if you want the Cholesky factorization to succeed, that floating point system should see that the matrix is symmetric and positive definite. What I mean is your smallest eigenvalue must be large enough. Okay, and also converting to a low precision floating point format, you are actually perturbing almost all the eigenvalues of your matrix. So if your eigenvalues are very small, the conversion will bump them onto the negative side, and it will lose its positive definiteness. So that's point number one. So Cholesky itself might not succeed. So point number two is it's a bit more technical in nature, which I will clarify as we go along the presentation. So CG might not work as well. So these are the two very important questions, two important issues one needs to address if we want to use this GMRES-based iterative refinement idea for symmetric and positive definite matrix. So to ensure that the Cholesky factorization succeeds, if you recall what I told was the eigenvalues must be big enough so that the Cholesky factorization succeeds. So the solution is quite intuitive. So what essentially you do is you just bump all the eigenvalues a little bit on the positive direction. But the catch is you just bump it enough so that the Cholesky factorization succeeds, but it doesn't lose a lot of information, because remember, you want to use them as preconditioners later. So if you want to perform a diagonal perturbation of a matrix, there are basically two ways of doing it. So the first one is just perturb the diagonal by some big number. Okay, so that is one way. Okay, and the second way is perturb the diagonal element based on its relative size. So what I essentially mean is, if your diagonal element has a very high value, then perturb it by a large value. If it's very small, then perturb it by a small value. So the intuition for this comes from the backward error analysis for the Cholesky factorization. I'll not go into too much of details of what those things are, but what I'd like to say is, so there are two methods here, right? So one is Pert A, where you just perturb the diagonal by a very large value. It's an absolute perturbation, if I may. And the second one is perturbed based on the absolute value of the diagonal. It's a relative perturbation. So if you measure how much each of them perturb the matrix, you can see the value here. So the first perturbation, which I call as Pert A here, essentially results in a large perturbation of your matrix. So you don't want that to happen, because you want to use these Cholesky factors later as preconditioners. And if you perturb them too much, and then the information about the original matrix is lost, and then it's not a very good preconditioner. So the second, whichever causes a smaller amount of perturbation is good. So just to drive the point home, let's consider a simple example. So where X means there can be any values, just to ensure there can be any values such that A is symmetric and positive definite. So now say you want to ensure that the Cholesky factorization of A is successful in double precision. Okay, so what I'm essentially saying here is you need to perturb it by almost this value, that is the maximum eigenvalue of A, but you don't know that when you want to solve a linear system. So you can approximate it using the largest element along the diagonal. So the amount of perturbation is largest element of the diagonal times the unit round off in which you want to perform the factorization. So in this particular example, so the largest value is 10 power 40, and the unit round off is around 10 power minus 16. So essentially, you'll have to perform a diagonal perturbation of this particular value. So if you do that, then 3, 3 is completely lost. Okay, so the conclusion is that even though there are two ways of doing the diagonal perturbation, a perturbation which is performed in a way that the relative magnitudes of the diagonal elements are respected, that's the way to go, because it preserves a lot of information. So among the two questions which I posed earlier, that is the success of Cholesky factorization and the convergence of iterative refinement. So all you will have to do is perform a diagonal perturbation, a relative diagonal perturbation, to ensure the success of Cholesky factorization. Okay, so for the convergence of iterative refinement itself, so one of the basic results which are employed to prove that the iterative refinement in fact converges is the backward stability of GMRES. But as it turns out, preconditioned conjugate gradient is not backward stable. So because of that particular reason, you can't guarantee that the iterative refinement would converge for an ill-conditioned problem. Okay, so but what would happen if the matrix is not so ill-conditioned? Would the iterative refinement converge then? So that is something which we can explore numerically as well. Okay, so that's what. Okay, so to explore this idea of solving a linear system using a symmetric positive definite linear system, I choose matrices from Sweet Sparse collection. The sizes of the matrix are pretty small, but we were testing out the numerical properties of it. Okay. And then the three precisions which we have used is half, single, double. That is factorization in half, matrix is given in single, and then you compute the residual in double, and similarly for half, double, quad as well. And since we are performing all our tests in MATLAB, and MATLAB doesn't have a native half precision support, so we have an emulator of our own which we employ to simulate half precision. That is what we call as CHOP. And to simulate the quad precision here, we use a software called as Advanpix. And then we test the iterative refinement with both, that's GMRES and CG. And to ensure the success of Cholesky factorization, so if you just see here, so you need to perturb it by some particular constant here, right? So this is n into n plus 1 into UL. So if you have very large matrices, then that particular constant is prohibitively large. So we take the pragmatic view of just check if it works. If it doesn't work, then redo the factorization. So as it turns out, a constant is equal to 2 is enough to ensure the success of Cholesky factorization. And we terminate the iterative refinement when residual is less than NU. Okay, so these are the properties of the matrices which I have chosen. It's not important what these matrices are. So you can just look at this particular column here, just to show that we have matrices of condition number of, we have matrices with a wide range of condition numbers. Okay. So this is the result when the diagonal perturbation is absolute. So if you recall, I don't see what is the relative magnitude of each diagonal element to do the perturbation. I just choose some maximum value, some big value, and perturb all the elements of the diagonal according to that. So these are the results. Let me explain what they mean. So the numbers within the parenthesis is the number of iterative refinement steps. Okay, so iterative refinement is itself an iterative process, so there will be a number of steps in it. So that is the number which is denoted inside the parenthesis, and the number outside is the total number of iterations of the iterative solver. That is total number of GMRES iterations or the total number of CG iterations. So one thing which you can observe is the number of iterations taken by both GMRES and CG are almost the same. And here, for these two matrices, CG doesn't converge simply because it's way too ill-conditioned. And if you recall, that was one of the qualifications which I made. So CG will not work when the matrix is very ill-conditioned. Okay, so the stars for 4 and 11, what they mean is if you convert those matrices into low precision, the smallest eigenvalue becomes negative. So that is one of the problems which I had mentioned earlier. So just to clarify, this is the first kind of perturbation where you perturb it you make an absolute perturbation. Okay, let's see what happens if you do a relative perturbation. So these are the results for it. Just for the sake of comparison, I'll go back once again. So these are the results for the absolute perturbation, and these are the results for relative perturbation. So these zeros here, what they actually mean is whatever answer you compute using low precision Cholesky factors itself is good enough if you want to have a single precision accuracy. If you want solutions of single precision quality, just the low precision Cholesky factor is itself good enough. Why it happens like that, maybe we can talk at the end, because I'd have to digress a bit for it. Okay, but you would need more number of iterations if you want to have a double precision quality. But the point here is both GMRS and CG, they perform pretty well for matrices of moderately high condition numbers, I would say. Again, so this 4 is a very ill-conditioned problem, but once again, you can see that even though 11 is an ill-conditioned problem, even then CG converges. So I'd like to summarize by saying that both GMRS and CG do well, but just compare the number of iterations here. So this takes a large number of iterations to converge simply because the quality of the preconditioner is not good enough. And here it takes less because this is a good preconditioner. Okay, just to summarize, performing a relative perturbation to ensure the success of factorization is a better idea than performing an absolute perturbation. Even though convergence of CG cannot be theoretically guaranteed, it works pretty well in practice for moderately ill-conditioned problems. If you recall, one of the precision combinations which I considered was half, double, and quad. Quad precision is not supported in hardware, so if you want to have performance, then that is not the way to go. So then the two combinations are half, double, double, and single, double, double. So we have tested them as well. So the behavior is pretty much the same, even in terms of the quality of preconditioner and the performance of CG and GMRS. But there is one issue which I have sort of jumped here. That is the maximum and the minimum numbers which you can represent in half precision or FP16 is quite small. That is, anything greater than 65,500 is infinity. So you need to do something to ensure that that doesn't happen. So you can essentially employ diagonal scaling, but maybe we can discuss that offline. Okay, but if your low precision format is bfloat 16 or FP32, that's not so much of a problem. With this particular algorithm, we have a way of solving a symmetric positive definite linear system using low precision floating point formats. So this can also be used to solve least squares problem, but you will have to use normal equation method for that. And many of us are aware, or most of us are aware, that normal equation is not solving a least squares problem using normal equations is not a very good idea because it's not stable. But for very well conditioned problems, it's okay because you can show that it's fine. Okay, but why is it a good thing to solve least squares problem, well-conditioned least squares problem using normal equations is, you can see that it is extremely intensive in matrix multiply. And if you're using hardware such as, say, NVIDIA V100, which has these tensor code features, then they are extremely good at doing matrix multiply. So any algorithm which is rich in matrix multiply is good. So this is a sort of a byproduct of the whole work. Just to conclude, the number of devices which have this low precision floating point support is increasing. So developing algorithms which can exploit the speed and energy benefits of these new hardwares is a timely question to be considered. So Cholesky factorization is extremely well suited for such devices because a dense Cholesky factorization is rich in matrix multiply. That is quite clear. But moreover, it doesn't require pivoting. So it's very GPU friendly. So if you want to implement this, then this is sort of the best thing you can do with a V100, I would say. Maybe I'm wrong. Okay. And if you want to ensure the success of the factorization, do a diagonal perturbation, or rather do a relative diagonal perturbation. That is a perturbation which is informed on the size of the element which you are perturbing. And CG, conjugate gradient based iterative refinement, even though it might even though you can't theoretically guarantee its convergence, it works well in practice. So you can find more details of this work in this preprint of ours. One other thing is all the codes I have made openly available. So I have a Git repository where I have put together all the basic linear algebra operations which you can do with low precision. So if you want to implement them, it's in MATLAB, and if you want to implement them and test how these things are for your application, please feel free to do that. Okay, so just to say once again, so this is a 2-part mini symposium, and the second part is tomorrow morning. I hope all of you will come once again. Thank you so much for your attention.